So today we're going to talk about cylindrical coordinates, and basically what they are they are a part of the 3D coordinate system. So let me draw a 3D coordinate plane first and help you understand what this means. So this is the z-axis, and then this is the y-axis, and then this part is the x-axis. So that's the origin, 0, or the pole. And then basically what we usually do is we plot a point. Let's say P is 1, 2, 3. So these x, y, and z, x is 1, y is 2, and z is 3. So this is called the rectangular coordinates. So these are really easy to understand visually because you know, oh, so I move 1 unit into the x direction, 2 units to the y direction, and 3 units to the z direction to get this point. But sometimes for calculations, it's better if we use cylindrical coordinates, so that's why they're invented, I think. So here we go. So basically a cylindrical coordinate also has 3 aspects. It's called r, theta, and then z. So from your experience with dealing with 2D coordinates, polar coordinates, that's what we call them, theta is an angle. And theta is an angle here also. So let's talk about r. So r is the distance that a point P is from the origin. So in terms of the xy layer. So in terms of this layer, how far is my point P from the origin? Theta is the angle that is formed between x and this line. So x rotated counterclockwise to this line that reaches point P. So how much degrees is that? So that's also an aspect. And then we have a new aspect, so it's z. And then z is basically still part of a rectangular coordinate. It doesn't change. So the z is still the rectangular coordinate thing. It just tells you how high up point P is. So let's say that's P prime. This is the actual point P. So this part's r, and this is theta, and then point P is just point P prime moved up z units. So z is still the number, let's say 3 or 1 or 2 or 3.2. It's still the rectangular coordinate form. So if you actually observe it carefully, you'll find the similarities between the cylindrical coordinates and the polar coordinates. And you also find the similarity between this and the sine cosine unit circle thing. So let me show you how that works again. So let's say I had this as my y-axis. That was my x-axis. This is my origin. And I have a unit circle. So this is a unit circle. Then at this point, the distance here is r, and the coordinates is the coordinates is cosine theta, sine theta. So it's a unit circle, right? So the radius is 1, so r is just always equal to 1. So here in our cylindrical coordinates and also the polar coordinates, r is not equal to 1. R can expand, like let's say r equals to 2, then we'll form a larger circle that's something like this. Yeah, something like that. That's the best circle I can draw right now. So let's say that's another r. So r is going to be equal to 2. So the coordinates here, if we use the polar coordinates, is going to be r and then theta. So it means that we're moving r units to the theta direction, and theta is this angle. This angle I labeled in blue is going to be theta. So basically I move r units And then what direction? In the theta direction. So great, I got this point. So here, the same thing actually happens. If you move back, this is basically the same thing as that, except for there's a new dimension z. So it basically tells you how high up P is. This thing is still the same. It's still similar to the polar coordinates. So our theta is essentially the polar coordinates. So yeah. So now let's try some converting from cylindrical coordinates to the rectangular coordinates. So let's say we have point P. It's, let's say 2, 5, 3. I just made that up. We want that, so that's rectangular. That's rectangular coordinates. We want that in cylindrical coordinates. So basically what we do is we first write the format of cylindrical coordinates to remind ourselves. So it's r theta z. We know that z doesn't change, so we know that we already know something. It's through this thing, pr theta z is pr theta 3. So what's r and theta? So we can ignore this, and then we just look at 2 and 5, and we just do the same thing like we did with the polar coordinates and the unit circle. So let's draw a 2D plane to visualize this out. So we've got 0.25, let's say that's 5, that's 2. So that's 0.25. And we want to figure out r, so that's this distance. So what is r? So essentially r, by the Pythagorean theorem, because that's a right angle, is r squared is equal to x squared plus y squared. So x is 2 squared. So x squared is 2 squared. Since the x coordinate is 2, y squared is 5 squared. So r squared is 4 plus 25, which is 29. So we know that r equals 29. So basically we can erase this all, and then we get that r equals root 29. So here we now know that r is root 29, and we only need to find theta. So what's theta? Well, if you can recall from the unit circles, then theta is basically, so if this were the unit circle, the coordinates, so the unit circle, the coordinates of this point here, or any point, would be cosine theta, sine theta. And now that r is not equals to 1, so the radius is not 1, the coordinates of this point is basically r times cosine theta and r times sine theta. So we know our r already, and we also know the value of this because it's just x, it's the x coordinate. So we can list an equation. R cosine theta equals, so the x coordinate is 2. So we know cosine theta equals 2 over r, that's 2 over root 29. And then we use a calculator to figure that out. Let me just type that in the calculator now. So that's gonna be arc cosine, arc cosine 2 over root 29. So that just gives us around 68. So theta is around 68.20 degrees. So now we figured out P. So this is 68.20. It's an approximation. We usually approximate 2 digits after so we usually round up to 2 digits after the decimal point. So this is our coordinates, our cylindrical coordinates for the rectangular coordinates 2, 5, and 3. So if you try to plot that, it will be essentially the same thing. So let's try another example. Let's try to convert 5, 6, negative 8 into cylindrical coordinates. So we already know z equals negative 8. So let's write the format of the cylindrical coordinates first. That's cylindrical. And then basically we already have r theta, z is negative 8. So we need r. R is easier to figure out. If we recall from here, r is equal to x squared. R squared is equal to x squared plus y squared, according to the Pythagorean theorem. If you're not sure why, you could skip back to the part just now and re-watch it. So r squared is going to be x squared plus y squared. That means r squared is 5 squared, 25, plus 6 squared, 36. 25 plus 36 is 61. Yeah, we double check that. Yeah, it's 61. And r is going to be root 61. So we've just figured out r. So you can replace that part with root 61. So now you need theta. So as you can recall from just now, if you're not sure, skip back to the previous part. R cosine theta equals the x coordinate here of the in rectangular form. So that's r cosine theta equals 5. We know r, right? So cosine theta is 5 over r. That's 5 over root 61. So we input that in our calculator. So if we input that in our calculator, then we'll get 5 over root 61. So we'll get that theta is approximately 50.19. Yeah, 50.19 degrees. So we can also write that in. That's 50.19 degrees. And this is the cylindrical coordinate of 5, 6, negative 8. Since 5, 6, negative 8 is rectangular coordinates, then p root 61, 50.19 degrees, 50.19 degrees, and negative 8 is the cylindrical coordinates. So in this lesson, we learned about cylindrical coordinates, and we've gone through 2 examples of how to convert rectangular coordinates to cylindrical coordinates. So basically, essentially, if you convert cylindrical coordinates to rectangular coordinates, we might do that in another lesson, but it's essentially the same process reversed. You can use the same theories, like r squared equals x squared plus y squared, and also r cosine theta equals 5. So thanks for watching, and remember to like, subscribe, and share. Bye!